This lesson deals with the SPICE macro modeling of the LM117 adjustable voltage regulator. You can find these notes in the ECE402 ebook in Chapter 8 starting on page 5. This particular model is one that I invented. I was approached by a national laboratory to develop macro models for off-the-shelf analog integrated circuits. I had to think about how could you create a model from scratch, and it's sort of like the things we do in the course where we invent a circuit or invent something to solve a problem. So I applied the same ideas to modeling, but my parts list now is not what's in the parts cabinet, but what's in the SPICE library. And there are some things that are really handy, like an ideal voltage source and controlled sources and nearly perfect diodes if you want them. So I started out trying to model the IC by mimicking a little bit of the chip. Remember there was a picture of the functional block diagram where we had actually what's called a Darlington pair. It's a transistor driving another transistor to effectively make the beta F much larger. This is needed because as the transistor grows in size, the value of beta F or beta DC begins to decrease. Well, in a SPICE model, I can make the beta F of this whatever I want it to be, so I didn't need two transistors, although initially I did start out with two, but realized I really didn't need it. Now when I took some of the measurements on the chip, I first started with the AC measurements and began to build the model to get that to work first. And that really had to do with this part over here. This is really modeling the op-amp that's inside the regulator. And this is creating a dominant pole with this capacitor and this resistor. And then I also added a 0 at higher frequencies because some of the curves rolled off as the frequency went up. Help me mimic some of that behavior. These two things here have to do with DC result. I'll talk about that a little bit later on. This diode was added mostly for DC effects because current can only go in this direction in an actual regulator, but in this particular model, current could come out the other way if I didn't have this diode here. This resistor was added to model some of the dropout voltage characteristics. What these are doing here is that this is modeling the short circuit current, and then this is modeling what's called a foldback, which is as the voltage at the input begins to increase, we need to decrease the current that's going through the part because there's more voltage across this pass transistor. We'll talk some more about this in today's lecture. So here's the specifications of that model. It has some of our standard parts of resistors and capacitors and diodes, but also these polynomial commands, and this allows me to create a product of terms or to actually shape a curve, and we'll see in a little bit what that has to do with current limiting. Now the development of this macro model I actually teach in another course in macro modeling. It's an independent study course if you're interested. What's in that course is part of this report that I wrote for that national laboratory way back in 1990. It documented how the macro model was created. I used the SPICE program a lot to begin to approximate equations. I'll send you a copy of this. You don't have to read it, but if you're interested in how a model was developed, this 37-page report will explain how I started looking at the problem and how I solved it. Let's go back to their notes. Take a look at some test circuits. This first test circuit is called ripple rejection. Given a regulator where you have an input that's coming from a full wave rectifier and a filter capacitor, you're going to have a DC average voltage and some ripple riding on top of it. How much of that AC voltage comes through the circuit and gets to the load? Hopefully it would get reduced in size, but the ripple rejection is a measure of that. One of the pictures in the data sheet is showing the ripple rejection versus frequency. So here's my circuit. I've got an AC input. I put a 1 volt here so I can just do a node voltage to get the transfer function. Have a series resistor here that's basically very small so that I got not a voltage source across these input, but something that place to drop the difference in voltage. And I got some resistor ratio here. It's going to give us a certain DC voltage, and then a load. The numbers that are here might seem a little odd, but it was the test circuit that I was doing when I was developing the model. These are the actual values of the resistors I was using. Let's take a look at the output. There's two cases here, one with and without this capacitor. This is one of the circuits that's in the data sheet, and there's a difference in performance. So this is actually plotting the output divided by the input of the regulator. Now, the ripple rejection is actually the reciprocal of gain, so I'm going to take the negative of that in dB. And so I'll get a number here that's positive, but the amount of gain that I'm having is actually a negative number in dB, which means it's a gain less than 1, which is good for a regulator. You don't want the AC signal coming through. Now, without adding the capacitor, you get a response that looks like this. Again, it's a frequency response. And this term over here is the value of the ripple rejection at high frequencies, and it was 2.12 dB in my simulation. Now, if you put a capacitor across the resistor R2, it does affect the ripple rejection, but it does cost more to put the part in. And you can see here that my rejection goes up. In other words, the value here is about 70 dB, which means that the gain is minus 70 dB. We are attenuating the signal, and then it eventually comes about the same value over here. We'll look at the data sheet a little bit later, and you'll see a very similar shaped curve in the data sheet. But in reality, when I measured the chip, I was getting results more like this, and I was fitting my model to fit the lab data that I had, and not the actual data sheet. I did initially, but I had a lot of trouble making the numbers fit. And I found that taking the measurements myself and then trying to fit that data was a lot easier because I knew exactly what I'd hooked up and what all of the probe effects were with my test fixture. If you take this out of dB by dividing by 20, raised to the power of 10, you're getting attenuation of 1.276. Key thing here, though, is that low frequencies, we are rejecting the ripple of the power supply, which is mostly 120 hertz, which is right over here. But as frequency goes up, we are letting some signal come through. This is troublesome in that if we have high frequency noise on our power supply lines, it's actually going to come through with a gain a little bit less than 1. This next test circuit is measuring the output impedance. And this is a little different in that the output impedance measurement that's in the data sheet is including the load that's here. Typically this is a lower value resistor. This is usually the equivalent circuit of whatever you got hooked up to it. So I've got the same circuit I had before, but now I'm going to put a current source here. And I'm going to vary that with frequency and measure the node voltage here, and the ratio of that voltage to this current, which is going to be 1 amp, it's going to give me the impedance looking back. Normally in a circuit we take the load off to find the output impedance, but this particular measurement has got it in. And again, this is something that's going to vary with frequency. So for low frequencies, when I don't include a capacitor, I'm seeing about 60 milliohms. So fairly low at 60 hertz, which is where a lot of my signals coming through with, but as frequency goes up, it eventually becomes about 3.5 ohms. Now you can lower all that by putting a capacitor across R2. This is a 10 microfarad capacitor. You can see that it dips more, and then up here it's not as much. Again, this becomes troublesome as the frequency goes up. My output impedance of my regulator isn't looking like more like a short circuit now, but just a low resistance. Now in developing the model, what I did was try to fit these curves to the parameters I had inside the model. So the things that were dealing with DC or current limiting and things like that, I just shut off and just simply used the op amp and introduced poles and zeros into the circuit so that I could match these curves. This is sort of the effect of a dominant pole, and eventually there's other poles and zeros out here. And so I was adding values of R and C's to create those effects. So my first pass on the model was to try to get the AC parameters correct. One other comment too, this is going to look very much like the data sheet, but not exactly. And again, what I wound up doing was measuring this myself and then comparing my lab data to the simulation and try to tweak the numbers so I get those to fit. Once I got the AC parameters working, I then started to focus on the DC parameters. And the first one I tried to model was the dropout voltage. So again, a basic regulator here. Take the capacitors off because this is going to be DC, won't make much difference. Applying a voltage here, I'm actually going to vary this from 10 to 15 volts in 20 millivolt steps, and then see how the output voltage at node 2 compares to the difference across the chip. So as I'm varying that voltage, we're going to start over here, and eventually you can see the thing levels off at about 9.562. Now if you calculate what you should expect to get, my reference voltage I measured to be 1.2782 for the test chip I was using. In the data sheet it says it's 1.25, and I'm just going to pick numbers here that would be very much like my lab data so I could get a good check on my model. And then with the two resistors I had, these are the exact values. I got 9.559 volts, and again, very, very close to this. This is when the input voltage was 15 volts, and this is where the input voltage was actually 10 volts. Again, I'm plotting the difference across the regulator. This is the differential voltage. Let me show you back over here. The difference across here. So here's V12. Now the dropout voltage is defined when you start out at the output and then you start to decrease the input until it drops by 100 millivolts. So again, every manufacturer will have some kind of testing that they're going to do, and this is how the dropout voltage is defined. And so I get about 2.1854 volts from my dropout voltage. So this dropped by 100 millivolts, and the voltage across the regulator is about 2.2 volts. Now this won't agree with the data sheet super closely, but again, this matched my lab data. And so I was following my modeling based on what I could measure. Very hard in a data sheet. Sometimes they don't show you all the test circuits, and you don't know exactly what they did when they took the measurement. And I get a little bit frustrated with the fact that I couldn't make my model fit the data sheet, and then I decided to just build everything and see how it turned out. The next parameter I tried to model was current limiting. Just like an op-amp, if you try to draw too much current out of an op-amp, it'll go into a current limiting mode. This regulator has the same feature, but an additional feature. As this voltage gets larger and larger, the voltage here is still the same. So the difference shows up across here. As that voltage increases, that current limit needs to go down, otherwise you're going to melt the transistors. So this has a current limit, and then what's called a foldback curve, which is to drop the maximum current based on how much voltage is across here. So same circuit we just did, except I'm going to put a 2 ohm load here now to draw a lot more current. And let's see what happens. So again, I'm going to be plotting versus the differential voltage across the regulator. And you can see here it came up to 1.0862 amps and then folded back as the voltage across it reached 60 volts. These 3 data points were actually what I curve fitted in the control source labeled E sub FB, which is E sub foldback. You can also see this on page 4 of the data sheet. I'll look at that a little bit later in the lecture. This next test circuit is looking at what's called a line transient response. Again, this is one of the pictures in the data sheet. But in my modeling, this was going to become a dilemma for me because I had modeled the AC characteristics first, then I built in the DC characteristics, but now we're going to see the transient, which is really an interacting between the AC parameters and the DC parameters. And I didn't know what to do in terms of the modeling, so I've just said, well, let me just run the simulation and see what it does. So what's happening here is that I have a DC voltage, and then I get a spike of voltage on the input line. What does that do to the output? So here's actually a 1 volt spike, mimicking the test that's in the data sheet, and watching what happens at the output of the regulator. So prior to this thing happening, we're getting about 9.5 volts out, and then we get this jump in voltage. It comes back down again, and then there's a corresponding jump and kind of an undershoot in ringing, and eventually comes back to the 9.5 volts again. And then on the back side does the same thing. This also is on page 4 of the data sheet. This doesn't exactly match the data sheet, but is similar in shape, and it's very close to what I measured. But I didn't do anything to get this effect. It was actually the consequence of the AC and DC models interacting with each other, which is great because I didn't know how I was going to solve that problem. This next test circuit is line transient response, but adding a capacitor across R2 and also adding a capacitor across the load. So let's see what's happening over here. So here's the previous case, just graphed again. So this is with C adjust not having a capacitor or the load capacitor, and you get the same undershoot and ringing, and then overshoot and ringing that we had before. So it's on a little smaller scale so the thing appears bigger. Adding these 2 capacitors, you do get a reduction in effect. But when I first hooked this up, my model went unstable when I hooked up this case, and I was really kind of puzzled by it. But I went back and looked at the data sheet, and it said to use an aluminum or a tantalum electrolytic capacitor here. Those are capacitors that have a very high value of ESR. So I went back in and said, okay, I'll include that in the simulation. And all of a sudden, everything was stable, and I began to get a curve that looked very much like my lab data. What's happening here is that when you have a pure capacitor here, this is again like a beta circuit problem. You get an op-amp circuit in here, and you basically have a lousy phase margin. In fact, you could look at this as a beta circuit problem. Putting this here creates a 0 and a pole actually into the equations of your circuit. And without that resistor, it doesn't work. But again, when you're putting a large capacitor across here, it's going to most likely be an electrolytic capacitor. There are some low ESR ones. You don't want to use this here because you actually need some resistance. Or if you put a low ESR capacitor, you have to add a series resistor so it doesn't go unstable. I was quite surprised about that. That really had me stumped for a while. So here I've included the losses of the capacitor. You could include them here. They didn't have much of an effect. Again, this looks similar to the data sheet. but not exactly, and again, match my lab data better. This next test circuit is called load transient response. And this is the case where we have a spike of current in the load. So I took our basic regulator again, but now I put a voltage source here and lifted this up to 8.562 volts and then brought it back down to 0. So when I'm at 8.562 volts, and I'm expecting here 9.559, the difference across the 20.1 ohms is about 50 milliamps. And then when this goes down to 0 volts, I've got the 9.559 across the 20.1 ohm resistor, and I get about 500 milliamps. So I'm getting a spike of current in the load. And again, this is one of the tests in the data sheet. I did nothing to the model, just simply modeled the AC and the DC correctly. And here again, I got results that looked exactly like my lab results because my modeling for AC and DC were correct, and the transient response was some mixture of those two. So here's my 50 milliamps jumping up to 500 milliamps and then back down again. And what you see again is here's our 9.559 volts, a dip down, and a little bit of overshoot and ringing, a shot up, and a little bit undershoot and ringing. Just like the data sheet you see on page 4. We'll look at this in a little bit. This last test circuit is putting the capacitor across here again and then putting a capacitive load here to filter out some of these responses. And so again, I plotted the previous results on a little tighter scale, so they look a little bit bigger, but it's really the same results I had before. But now adding this 1 microfarad capacitor and then this 10 microfarad capacitor with a series resistor, that was reduced significantly. And you'll see the same thing is true in the data sheet. Again, my data sheet, and this won't be a perfect match, but this did match fairly closely to my lab results. Again, I didn't do anything special for the transient response, but just simply got the AC and DC correct, and then these just became a consequence of that. Let's take a quick look at the data sheet again. And let's go to page 4. And you can see here's that fold back result. Here's our dropout voltage. We took some measurements on that. Here's the ripple rejection versus frequency. Again, a similar curve, but not exactly with what I simulated. But again, my lab data and my simulation match pretty carefully. The output impedance versus frequency, the line transient and the load transient with and without the capacitors added. Also in the model, I did one more thing. When I finished the model, I had talked to the people I was doing the model for, and they tested it and said, oh, it doesn't work. Okay, what do you mean by that? When we turned the circuit on and off, it didn't respond correctly. And my response to them was that you didn't tell me you were going to do that. But whenever you shut off an IC and power it back up again, the transistors don't go active or saturate or cut off instantaneously. They go through a sequence of passing through those states. And so I then went back and took data measurements on the part and then tried to figure out what was happening with the turning on and off of the power supply. And this is part of the report. If you turn to the report on page 35, you can see some of my lab data. For the regulator that we were looking at in our examples, I was putting a 15 volt source on the input. Now what I've done is I've changed that to a triangle wave, starting out at 0 and going up to 15 volts and coming back down again. So here's 20 microseconds, 40 microseconds, 50 microseconds, and then right back down again. Fairly rapid increase and then decrease in the power supply. Here's the output of the regulator. Kind of overshoots a little bit, then comes back to the reference voltage about 9.5 volts. I blew this up and printed it again below. So a little better see the overshoot here and then the ringing that occurs on a smaller volts per division scale. What I needed to do was to change the model so I could get this kind of behavior. So let's go back into the notes. Let's go back to page 5 where we had the model. And what I had to do is shut the amplifier off for part of the power-up cycle. In other words, things that were in the 50 microsecond range. And so I played with like a few things, but what I found that worked was putting a diode across here. So I first turned it on, the diode conducted and shorted out the cap, and eventually the currents in here got smaller and this became an open circuit. And we're back to the model that we created. So let's see what happens when you do that in the model. So we go to page 34. So this is the model we were talking about, but I've added a diode across that capacitor. That's not in the model that I was showing in the notes. And here's what happened to the output. So here's my input going from 0 to 15 volts and back down again. again on a 50 microsecond scale, 100 microsecond cycle. And sure enough, here's my response. It overshoots and then rings and comes back out again. So it looks exactly like what we had on the lab data. So that was a good fit. That was surprising, but I had to think of playing with ways of kind of shutting off part of the amplifier. If you look at the pages before this, you'll also see some of the lab data that I did. Here's the output impedance measurement, the SPICE simulation that we showed, and then here's the actual lab data marked underneath it. Not a perfect fit, but pretty close. If you go to the previous pages, you can also see some of my other lab data. Again, this report you don't have to study. It just shows some of the work involved in creating the model. And again, it's quite long. It's 37 pages and represented about 3 years of work. If you want to take a look at it, it's an interesting part. But again, it's part of another course that I teach in modeling. So this is the SPICE macro model of the LM117.